All right, recording is rolling. So it is Monday, November 14th. Welcome back from a long break because I had a couple days off from hurricane, and then there was Veterans Day, and then Saturday and Sunday. So I haven't seen you guys in quite a while. But here's the top scientist for energy. So awesome job if you're on this list. I have not handed the quizzes back yet. I'm still waiting for a few to come in, but I'll eventually get these back to you guys, and you guys can still do quiz corrections like normal, but it's going to have to go on the fourth interim. You guys know that the third interim is like ending like right about now. Grades are due tomorrow at 5 o'clock, so definitely check all your classes, make sure that all your grades are in, or all your assignments are turned in, right? So if you're missing anything, then definitely get it in today, because anything that you turn in tomorrow, can't 100% guarantee get it in time, just because it's a time issue. I'll be like teaching my classes, and same thing for all your other classes too. So yeah, so make sure you got all your stuff turned in today. All right, so we are continuing momentum. Now last week, I was using this page to go through like a checklist of ideas, solving problems as we went along. We've got about halfway through. Then on Tuesday, we took that day to do a collision lab, but we're going to pick up today. And these last few problems, here's the main two ideas. Coefficient of restitution, so how bouncy is something. It's a physics way to quantify how bouncy is something, called coefficient of restitution. And then impulse, delta P, impulse, like a change in momentum. Then the last about 10-15 minutes of class today, I'll set you guys up with a short lab where you're going to get these bounce balls, and you're going to figure out like how bouncy is the bouncy ball. Right? You'll be able to quantify that with nothing except the ball and a meter stick. So if you got the ball and the meter stick, you'll be able to calculate how bouncy is the ball. So do that last few minutes today. Okay. How about the rest of the week? So tomorrow, I'm going to go over conceptual questions with you guys, and this will be with Kahoot. Now, you guys have these questions printed out. You guys remember it's this page that we're going through, or we're going to go through again, like the second half of these today. Printed on the opposite side are 20 conceptual questions related to momentum, and we're going to go over those tomorrow. Okay. Some of those questions are going to show up on your next quiz. Okay. Actually, speaking of which, here's how the rest of the week is playing out. So Wednesday, I'm going to take Wednesday. I'm going to have you guys in teams on Wednesday. We're going to do something a little bit different. That'll be a review type day. I'm going to give you guys another page that looks a lot like this, just the numbers will be different. And this will be practice problems for you guys. So you guys can make sure that you know how to apply these equations and solve these, right? And walk around and answer any questions you guys have. Then Thursday, I still want to do the take home, or sorry, the in-class quiz with you guys. Okay? I told you guys last week I was planning an in-class quiz for this coming Thursday. I know we're short a couple of days, but I shifted some stuff around, going to get some things, and we're still going to do this. So that's honors. Here's you guys. Okay. Here's you guys right here. Okay. Conceptual physics. Okay. Right. So today we'll do some notes and then a lab at the end of class. Okay. Tomorrow's going to be conceptual questions. Wednesday is going to be extra practice review. I'll answer any questions you guys have. Right. Now, the in-class quiz on Thursday is going to be open notes. So any notes that you guys took last week, any notes that you guys take today, any notes you guys take tomorrow or drop down on Wednesday, you can use any notes that's going to help you out on the quiz on Wednesday or Thursday. Okay. And I'll tell you exactly what's going to be on the quiz on Thursday. It's going to be about half of it's going to be these conceptual questions, and about half of it is going to be questions that look a lot like these. Right, I just copy pasted the questions and like changed some numbers, but it's like same scenarios. Okay. Then Friday, I've got another activity lined up just to take us to Thanksgiving break, because you guys know Thanksgiving break is in 1 week. And if you miss Thursday for whatever reason, then that can be a makeup day for the quiz. Okay, so you guys get what we're doing this week? All right. So let's all set up here. All right, and let's get going. So here. All right. So we're working on this page, and we got about halfway through it. Okay. Now, I know the last time you guys saw this was last Monday. It was a while ago, so we did a quick crash review with you guys, and then that'll lead it straight into the next part of the story. Okay. So we're looking at momentum. Okay. Now, momentum is mass times velocity, right? So how massive is something, how fast is it moving, right? And this is also a vector quantity, so directions matter. And the scenarios where you care about momentum is collisions, because it turns out that momentum is conserved in the universe a lot like energy was conserved a couple weeks back, right? But momentum is mass times velocity. If you have that mass times velocity for a bunch of things that are colliding, before and after the collision, momentum is conserved. Here's what it looks like right now. This is all in one dimension. I'm not going to do anything in 2 dimensions, so don't worry about that. But everything's just in a straight line, head-on collisions. Mass times velocity to the individual bits. Add them together before the collision, after collision, they have to equate. If you know a number of things, you can solve for stuff. Okay, that was like number 3 and number 4. Number 3 and number 4, just straight general conservation momentum. Okay, then there were different kinds of collisions. Okay, so like collisions might be really bouncy. There's a pretty bouncy type collision, right? Or not. Here's sure. Right. Wow, that one doesn't bounce at all. It just glides on sticks. That has a name. That's called perfectly inelastic. So perfectly inelastic is like one boundary condition, like one extreme form of collision you can have. That's 2 atoms collide and stick together. Okay? And if they collide and stick together, that means there'll be one giant mass with one common final velocity after the collision. So you can just take the original setup and then modify it a little bit. And that looks a lot like number 5 that we also did last Monday. Okay? But you know what else this also solves is you guys remember I played that Magic School Bus clip for you guys, right? So pitcher throws the ball and she got kicked back the other way. And we're like, how fast was she going back towards second base? Well, if you know her mass, the mass of the baseball, and the speed of the baseball towards home plate, that's enough information to solve that question, how fast she head back towards second base. So we solved that last week, so it's in your notes. But it is this, but in reverse, because if you filmed that and you ran the film in reverse, like, it would look exactly like a perfectly inelastic collision where she and the baseball come together and then they're just sitting at rest on the mound. And then forwards in time, just turn back this. So you can just apply this in reverse. And so we did that, but we also applied it to number 6, which was a grenade exploding. Because a grenade exploding, it's the same type scenario. If you run that film in reverse, it also looks like this. Then forward in time. Okay? So you can still run, it's the same collision physics, it's just like a reverse collision. Okay? That's going to bring us to number 7. Number 7 is like the opposite extreme. Right? What if it's not perfectly inelastic where they stick together? What if it's like as bouncy as you could have, like perfectly bouncy? Well, that's the name too. It's called perfectly elastic. And it's hard to find, exact true example of this, but this one's pretty close. This is probably as close as I can get. Okay? That's probably as bouncy an example as it can have in this group. Okay? Okay. And for something that's perfectly bouncy, perfectly elastic, right? Not only is momentum conserved, here's your general conservation of momentum, right? That's always true. It's just like law of physics, okay? But also it turns out that for perfectly bouncy specifically, perfectly elastic, kinetic energy is also conserved. Right? No, that's only for this type of collision. Okay? So that's your 1/2 mv squared. Add all the bits together before and after the collision. It happens to be the case. Okay? Now, if you take these two as a system of equations, this right here is a general expression for the solution always to the system of equations. I mean, you could run a bunch of numbers, you could check me on this, but that's always going to be the case. And here's what I always tell my students too is if you take physics in college, some of you guys will, if you're going to be like, go off to be engineers or sort of deal, they might have you solve perfectly elastic. But this expression, really hard to find on the internet and also not in very many physics textbooks. So probably a good idea to hold on to this paper so that you have like this general answer, save you definitely a ton of time and a ton of paper. But let's go ahead and apply that to number 7. So 2 objects collide perfectly elastically. All right, what's the final velocity of object A and stuff like that? So all I'm going to do is take the answer right here, which would normally these two, if you solve the system equation, it takes lots of paper and lots of time, but taking it straight to the answer, right? It's got a head-on collision. I'm saying velocity A post collision is, and it's always this giant fraction. Got velocity. Well, here I'll just start plugging numbers in. So velocity A initial. On here I have 5 meters per second on my paper. 5 meters per second. Okay, you guys have something. So 5 meters per second times the difference in masses, mass A minus mass B. So for me, that's 1 minus 2 kilograms, 1 kilogram minus 2 kilograms. You guys might have different numbers than I do. So 1 kg minus 2 kg. Okay. Plus 2 times, there's always a 2 here, mass b times velocity b initial. So mass b is 2 kilograms, 2 kg, and velocity b initial, I have as -3 meters per second. Now the negative is important. Okay? The fact that object A has a positive velocity and object B has a negative velocity, okay, that means that these two objects are kind of like this, right? Head straight toward each other. Bam. Okay. Opposite directions. Remember, these are vector quantities. Okay, so the direction matters. Okay? And then all divided by the sum of the masses, MA plus MB. So that's by 1 kilogram plus 2 kilogram. Okay, so let's just pop this all in the calculator and see what is the post-collision velocity of object A. Okay, so you got 5 times 1 minus 2 plus 2 by -3, all divided by 1 plus 2. Okay. And velocity A post-collision is -5.67 meters per second, okay, which is an answer choice. So good with that. Okay, there you go. Okay. Now, if you're here, while you guys are jotting that down, calculating yours, adjusting that, sort of draw this out. I got object A is 1 kg, object B is 2 kg. They were headed towards each other, like 5 meters per second and -3 meters per second. They bam, glided off each other. And I know that object A rebounded even faster than it was coming in, which when you guys were setting up the collision cards last week, you may have seen that some of those cards could speed up if you had the right masses, the right conditions. So you got -5.67 meters per second. It's hard to make things speed up from collisions. You can do it. Okay? It helps to have an elastic collision, because it's not going to happen with inelastic, but elastic it can. Right? And the other object is heavier in this case. That's okay, right? But if you keep a real close track, you might notice that there's one piece of information that's still missing from this that we haven't quite answered, right? Which is, what is the post-collision velocity of object B? Okay. Now, just to save us some time, because again, we're missing a couple of days, so I'm going to cut a little bit from what I would normally tell you guys. But I do want to tell you guys 3 different ways you can solve for the post-collision velocity of object B. And no matter how you do it, you're going to get the same number. Because different paths through the forest should all lead to the same answer. Right? One way you could do it is you could take, because you know everything except for that, you could just go back to general conservation of momentum. You say, well, I know all these things except for post-collision velocity of object B. So plug in all these numbers. You got one equation, one unknown. So for that, bing, get some number. Get how fast does this rebound from that collision? Option 2. Well, you could just resort to also conservation of kinetic energy, because it is perfectly elastic. So this is true just for that condition. And same story, solve for that. One equation, one unknown. Okay. A third way you could do it is you could look at this general solution here, and you could just change the definition of what's object A and what's object B. Right? It's a little bit creative way to do it, but you could say VB final equals VB initial times mass B minus mass A. You know, just like swap all the subscripts. Right? Go about it that way. Okay. And again, no matter how you do it, you get the same answer. Right? Okay. You guys get that? All right. Actually, right, number 9 go together. They both involve coefficient restitution. Actually, what you do is save those for last, because that's going to lead straight into your lab. So let's do that. Let's skip down to number 10 and 11, which are also very similar idea. We're going to come back to coefficient restitution. Right. Now, number 10, number 11 involves something called impulse, right? Like a change of momentum. There's a bat hitting a ball, okay? And well, I asked different questions because 2 different questions here, but here's the general principle. If you apply a force for some time interval, okay? So here's a force versus time graph. This is just a graphical way of looking at this, but I'll show you guys the equation form. It's going to let you solve the equation, those questions, okay? All right, so turns out that the area under force versus time, or if you apply just a constant force for time or an average force. So see this dashed line? You guys see like a dark rectangle here? If you did base times height of the rectangle, that'd be like an average force times a time interval. Delta T is time interval. That could tell you impulse, which is going to be in Newton seconds or a kilogram meter per second, okay, for change in momentum. Okay. Or what's the deal with the triangle here? Okay. Now this light green triangle, this dark green rectangle have the same area, so they're both talking about the same impulse, different points of view. Okay. more realistically, here comes the baseball, here's the bat. You see a bat and the ball, right? Is if you had like slow motion, right? They would start to make contact, then they would shoot. There'd be like a tiny time interval where they push against each other, and then the ball would like rebounds. Okay. So as they start to make contact, it's a small force, and the force builds up, up. And then here the baseball starts to reverse direction, and then it leaves the bat right here. Right. So real collisions, you get like these triangle type looking graphs, but whichever one you go with, right? Okay. You can calculate impulse, change of momentum. Now let me put that in equation form for you guys. Okay, so equation form goes like this. Okay, so impulse is a change in momentum. Okay, and impulse I can write is like delta p. Right, but that's what this is, right? Change in momentum. You guys know that change in oftentimes this is represented with the Greek letter delta. It looks like a triangle. Okay, and lowercase p is momentum. Oh, so change in momentum. And I've always been in the habit of putting a little vector arrow above the p to remind you guys that that is a vector quantity. Okay. Okay. Well, you guys know that just plain momentum is mass times velocity. So if you're changing the momentum, and if you have a constant mass, then it's mass times change of velocity. Same thing. Okay. Now before I go trudging on with this, I will give you guys like counter examples of what I just wrote, right? Because this is not necessarily universally true, right? You could have a constant velocity, but a changing mass. For example, if you have like a conveyor belt, you're like dropping jelly beans on the conveyor belt, you want to keep the conveyor belt running at a constant velocity, you might need to apply a force as the mass is changing, right? You have a grocery carton jumping groceries on it, right? So yeah, that's a counter example. I don't think you're ever going to run into that in this class, right? So what you will have is a constant mass, but changing velocity. Hey, like a ball, bam, being hit by a bat. So it's changing its velocity. Right? But hey, change of velocity. You guys know that that's going to involve an acceleration. And if you see an acceleration, there must be a what acting? A force, right? Oh, that brings us back to like this graphical look at it. That's why there's a force applied for some time. In fact, that's exactly what you need. You need a force applied for some time interval. Time interval I'm going to represent as delta t. You guys see delta t could be like the time interval. You guys see that? Okay. And this force is really an average force. I need to specify that. I'm going to put a subscript average. Right. So I'm talking about this force right here, right? Which is really referring to like this rectangle type shape. Right? Is that right? Right. So there you go. Right. If you apply a force for some time interval, say newtons times seconds, that's going to result in kilogram meter per second, like a change. So all the units are also consistent. Right. Kilogram meter per second, kilogram meter per second is the same thing as newtons times seconds. It's the same thing. Okay. So I thought there. All right. So number 10, number 11 are just different variations on applying this impulse setup. So number 10 says a bat's hit by a ball's hit by a bat. Suppose you know the mass of the ball, probably pretty easy to get. And suppose you also figure out what the force is from the bat and the time interval, which is a tiny fraction of a second. Can you figure out the change of velocity of the ball? So let's go ahead and knock that out first. So if I've got a for delta V, okay. So I've got a mass of 0.15 kilograms, and I'm solving for what's the change in velocity of the ball. And I know the force. Now this is an average force, right? Okay. And a time interval, which is a tiny fraction of a second. Okay. Then you can solve that. You guys see the one step you need is just to divide down the mass. Divide down the mass. Right. So delta V is 190 newtons, 0.03 seconds, divided by 0.15 kilograms. Okay. Let's see what is the change in velocity of that ball. 190 times 0.03 divided by 0.15. Looking at 38 meters per second. Right. Now, notice that that is a change in velocity. That's not any specific velocity. And I'm bringing that up because this is kind of an ambiguous scenario. This could apply to a lot of different scenarios. For example, if the ball is just sitting on a tee, you guys know what a tee is, right? It's just, you sit a little plastic tube, you just sit the ball on top of it, it's just sitting there, rest, and the ball is, bam, you just hit it off the tee. It might go from 0 to 38 meters per second. Well, that would be a change of 38 meters per second. But you know what else would work? Is what if you throw the ball at the plate at like 10 meters per second, and it's hit back, bam, at like 28 meters per second. You guys see 10 to the left and 28 to the right is also a difference of 38, right? Here, let me throw that on a number line. you got zeros, zeros right there. If you got -10 here and positive 28 here, you guys see the difference would be like 38 units, right? Is that okay? So this could be like many different scenarios could play out with like these numbers. Okay, is that right? And finally, number 11, which is a very similar scenario. It's the same story. Just change what you're solving for. Right? Ball hit by a bat. It's the same ball. Right? But now, what's the force if you actually do know the change in velocity? I do want to do one little different thing with this. So we got here. We had to first reverse the impulse equation. We're going to put L delta T on the left. You guys will see why in a minute. Okay, equals M delta B. Okay. Vector. Okay. I'm going to solve this in terms of variables first, which again is only one step. If you're solving for the force, that's the question. What's the average force? What's the average force? Okay. You say I'm just going to take the time interval and divide it now. So I'm going to say force is mass times delta V on delta T. You guys see that? Okay. Why did I do that? Right. Well, because this is something that you guys have seen before. Oh, F equals M times. Hey, what is delta V over delta T? What's that called? The rate change of velocity. Acceleration. Is this force equals mass times acceleration? Yeah, that's Newton's second law of motion. You guys see Newton's second law of motion? You guys see how the impulse formula is just one step away from Newton's second law of motion? Actually, this is closer to how Newton thought about his own second law of motion. He said if you push or pull on something, what a force is, it will cause a time rate change of that object's momentum, which is what this is kind of saying over here. Okay. Right, but anyway, let's just pop in the numbers and get a solution here. We still got the same baseball, 0.15 kilograms. I've got a change of velocity of 41 meters per second, which again could be a lot of different scenarios, right? Different pitching speeds, different rebound off the bat, but let's just say the numbers like pan out to be that change. Okay, maybe you threw it at 20 and it rebounds at 21. -20 minus 21, right? We had a change of 41. Okay. Right. And then this is all in 0.03 seconds, so very tiny time interval because there's only a tiny fraction of a second that the ball and bat are in contact with each other. So what is the average force from the set of numbers? 0.15 times 41. There we go. It's better. 205 newtons. Okay. Again, that's just an average force. And that's all I asked you for. But if you wanted a bigger context, we're talking about this right here, right? So the maximum force is probably about double that. But there you go. Average force. Okay. From the bat on the ball. Okay. You guys good there? We're good? Okay, so now let's go to the couple of problems that I skipped, number 8, number 9, because this is going to lead straight into the lab that I'm going to have you guys do at the end of class today. Okay. Okay. These both involve coefficient of restitution, but I mean, just at a glance, you can tell that it's pretty different perspectives, right? So one has to do with like velocities, one has to do with like some about like a drop height and a rebound height, right? But they are related to each other. Okay? So the sort of definition of coefficient of restitution, which again gets to like how bouncy is something, is this right here. Two objects headed towards each other, head-on collision, bam, then they rebound. Okay. Now, you could say, well, what is the difference in this context that delta means difference? Okay, and it usually means change, but in this context, it's difference. What's the difference in velocities post-collision if you do that minus that, right? And careful with sign changes because if you have a positive minus a negative number, it's kind of like adding, right? So be careful with that. Okay, compared to before the collision. So if you do like the difference before, okay, here, well, we're about to run some number examples, but big perspective here, right? Okay, and then if you take the ratio, okay, now this is a way you can quantify how bouncy is something. Okay, how about this? What if the two objects collide and stick together? Wouldn't that be like perfectly inelastic? Okay, if they do that, what is the difference in velocities after the collision? It would just be 0, wouldn't it? Right. Maybe they're stationary, maybe they're moving together, but the difference of velocities would be 0 either way. Okay, so 0 divided by anything would be 0. So coefficient of restitution of 0 would correspond to like perfectly inelastic. You see that? And if they were like perfectly elastic, so here's perfectly inelastic. Okay. If they were perfectly elastic, which is pretty close to this, okay, then the difference in velocities after is the same as what it was before. Right. So this would be like a 1-to-1 ratio. Right. Now there's one little technical note I want to show you guys here, point out, which is guess how I did b minus a on top and a minus b on the bottom. Right. Because if you were consistent, if you did b minus a and then b minus a, this would naturally come out to be a negative number, and it's always negative. So it's like, well, right. If you want a positive number, which is a little easier to talk about, you can either slap on a negative sign. Some textbooks do that, or some textbooks just reverse, and they do it the way I printed here: b minus a and then a minus b. Right. So that it'll take something that would be negative and always makes it positive. Right. So coefficient of restitution, how bouncy is something, difference in velocities, post collision compared to pre collision, is always bounded between 0 and 1. Right. So 0 is like a perfectly inelastic. And then 1 is like boing, 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 perfectly elastic. Okay, better. Okay. All right, so let's run some numbers here for number 8. Okay, number 8. Okay, because I'm actually gonna let me do this. I'm gonna make up my own example. Do my own example here. Okay. I'm gonna do a ball bouncing off the floor example because that's similar to the watts that I'm gonna have you guys do. Okay, this is boing. Okay, the ball like rebounds, something like that. Okay. So what if this ball has a crash speed? I'll call this V crash of like 10 meters per second, and then it has a rebound speed, V rebound, of like 7 meters per second. Okay. Now, one other detail: the fact that it changes direction. I have to slap a negative sign on somebody, so maybe I'll call up negative and down positive. How about that? Okay, so is that all right? Right. Okay. Do you guys see a change in velocity of like 17 units? Right. So -7, +10. That's a difference of 17. Okay. So that's just a side effect. That might have something to do with more like impulse. If you took the mass of the ball and multiply by 17 meters per second, that would give you the impulse. Okay, that's not exactly where I'm going with this question or your lab though, but could do that. Okay, I'm interested in coefficient of restitution. So coefficient of restitution. What is the difference in velocities post collision compared to difference in velocities pre-collision? Right, and we're just gonna, well, here's another way to absolute value, so we'll always make it positive too, right? Okay. Now, the example that I'm doing here, the floor is not, the floor could be like the entire Earth, which basically has a velocity of 0. You know, I mean, we're all moving with the Earth, so that's our perception, right? Like our frame of reference. Okay, so I could do -7 minus 0. And then make it positive, so just call it 7. And then compared to pre-collision, be like 10 minus 0, right? Or just like 10. You guys see that? Okay. So this would be like 0.7. Is that right? Okay. And hey, that's exactly like inside the boundary conditions that I gave you. Okay. Because if it was this, okay, the final velocity difference between this and the floor, or this and the ground, this and the earth would just be 0. 0 divided by anything. We're talking about exactly this right here, right? And suppose I have like the world's bounciest bouncy ball, like a boing, and it's just like boing, 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 and then you just like leave this in a room, come back 1,000 years later, and so like boing, boing, boing. Okay, well, that would be like perfectly bouncy. It would be like 10 over 10, which would be exactly 1, right? Which is a really ideal scenario, right? Guess that too, right? Okay, now how can you really like get these speeds though with just like physics equipment? Well, I mean, I guess you could use that speed gate if you like bounce this like right inside the speed gate, something like that. Okay. But there's a more fundamental way to get it with just a meter stick, because I bet you guys remember what these speeds are like based on drop heights. Suppose this was like H rebound, and this was like H drop, capital H, like a drop height. So you got a drop height and a rebound height. Right. Wouldn't these speeds be related to these? Well, this crash speed is related to this drop height, and this rebound speed is related to this rebound height. That true? Okay. And there's a relationship there that you guys have seen multiple times before in this class. You guys saw this way back in the day with kinematic motion. You guys remember this third kinematic formula? Okay. Something starts from rest, say if you drop something, then wouldn't the crash speed be the square root, because you have to square root both sides, right? Get rid of that square root 2EX. Isn't that like square root 2GH, square root 2GH, right? And then the same is true for the rebound, right? Or you might remember from conservation of energy. If you go from potential energy to kinetic energy, right? It's the same thing, right? Which is that the V is going to be the square root of 2GH. Now it's that in general, right? Well, if coefficient of restitution, we're interested in the ratios of these differences in velocities, and before we're just treating as having a velocity of 0, then I can say coefficient of restitution is the same thing as square root 2GH rebound compared to square root 2GH drop. Just like that. That also be true? Okay. See, if that's true, ooh, do you guys see some stuff that's going to cancel out? Is that true? Okay. So coefficient of restitution is, okay, you can take the ratio of the rebound height to the drop height, and then take the square root of that ratio. Okay. Let's do some numbers. Let's say, for example, if the drop height was like 100 centimeters, and let's say the rebound height was like 49 centimeters. Okay. So let's feed the numbers in here. So square root of, okay, got a rebound height of 49 centimeters, got a drop height of 100 centimeters. Okay. Looks like the centimeters all cancel out. You could have done meters, but it's still be the same ratio. The units cancel out. What's the square root of 49 on 100? That's 0.70. Okay. Guys got that? All right. And then that's also exactly number 9. Right. We just did number 9 right here. That is number 9. I just wanted to write it for you guys, show where that's coming from. So can you guys do that real fast on your page? Okay. So here, I'll do it with you guys. So I'll do a square root. My rebound height is 0.65 meters divided by drop height is exactly 1 meter. So I have a coefficient of restitution on my paper of 0.81. Okay. Bam, done. Okay. Okay. See what we're doing here. Okay. And then well, with number 8, I bet you guys could just feed these numbers very simply into this expression and get the answer for number 8. You guys can do that too, right? Okay. All right. All right. So we're good there. All right. Lab time. Here, let me get you guys paper. Make sure you guys got paper here. We get the paper. Nice. I'm gonna have you guys draw a table, and then bounce some balls, fill up this table, and then turn this in, and that will be a wrap on today. All right. All right, so you guys got some rulers on your desk. You guys ready to draw a table? So write your name on your paper. Okay. Did everybody write your name? Right. You guys got a name? Okay. And this is going to be the coefficient of restitution lab. Right. Okay, that's a fancy physics way of saying like how bouncy is a ball. Right. What's this? Let's go. All right, let's do 5 columns. How about that? 5 columns. So yeah, we got us all at I think 12 minutes in here. Right, so this would be perfect time to do this. So pick a ball. No, there are a bunch of balls scattered around the lab area back there. I mean, I've got some examples here, but I have a whole bag of different balls like this back in the lab area. So pick your favorite one, okay, with your classmates, and go capital H to be drop height. You can do this whole lab with just your favorite ball and a meter stick. Okay, that's all you need. Okay. This could be in either meters or centimeters. So I'll let you choose, but pick a unit. Okay. Then you lowercase h could be the rebound height. Okay. So you got drop height, you got rebound height. Okay. There you go. Make it a table. All right. Take the ratio of those two heights, okay, which will be somewhere between 0 and 1. And finally, here's what we're actually looking for. Okay. The coefficient of restitution is equal to the square root of that ratio. Okay. And I bet that as long as you're using the same ball over and over, you could pick different heights. Here, I'll do some examples. You don't have to use exactly these numbers, but you might do 60 centimeters, 80 centimeters, 100 centimeters. Again, pick your favorite drop heights. You don't have to do those 3 exactly, but those would be pretty good ones. Okay. See what is the rebound height from each case, and I bet you're going to get the same coefficient of restitution between your favorite ball and the tiled floor. Okay. All right, you guys good there? All right, then just turn this slab into that grade tray by the end of class, and that is a wrap on today. Okay, and then remember tomorrow we're doing Kahoot with conceptual questions, and then Wednesday is going to be more practice, and then Thursday is the quiz day. All right, so just turn this into the grade tray by the end of class.